Hello, welcome to Advanced Training for Altair Breeze. Today we're going to look at a trace of Altair HyperWorks Radios. This application has been set up to illustrate some of the I/O issues that our customers face on a regular basis. Looking at the I/O summary, I can see this application ran for an hour and 22 minutes. This is as expected, and it does just over a minute of bad I/O, which is 40 seconds of 0-byte I/O operations, 26 seconds of small reads, and 10 seconds of backward seeks. Let's switch to the mount point view to see where that I/O is taking place. So I can see that most of the time is spent at the root file system, with 46 seconds spent reading, 26 of which is small reads, and 31 seconds doing seeks. Let's look at the number of calls. There are relatively few open calls, and so from this I can assume that the reads and seeks are being performed on a small number of files over and over again while they're being kept open. It's always a good idea to look at the number of reads and writes and compare that to the number of open calls, because applications often open a file, read or write from that file, and then close it again over and over again, sometimes writing just 1 byte at a time. This is extremely inefficient for shared file systems, so I always look at the open calls. So let's switch to the files view in order to identify those files that are being read over and over again. If I sort by the number of reads, I can see immediately which 16 files are being accessed over and over again. There is 1 write to each file, 2.5 million reads, and a little over 3 million seeks. The I/O summary said there were mainly backward seeks, which are less efficient than forward seeks. So it looks like the application is reading to the end of the file and then seeking back to the beginning. The I/O summary also said there were a large number of 0-byte reads or writes. These usually happen when an application reaches the end of a file, and so that, I would guess, is triggering these seeks. If we switch to total latency, you can see that a few seconds is spent reading and seeking each file, so it's not going to impact the runtime of the application enormously, but this is something that could be tidied up in order to make Radios just that little bit more efficient. Now, I always like to check the dependencies of an application. Since there are lots of files accessed by Radios, I'm going to look at the directories view, which groups results by directory. You can see Radios is installed in /opt. That's where we have most of the dependencies. Radios also accesses /proc. The proc file system is used to collect information about running processes. And you can see that Radios is storing some hidden files and temporary files in the home directory of the user that ran this application. You can see it also accesses a Tickle installation from another's user directory. That is not expected, and so that is something that I would go back to my colleague about. This is a common issue found when looking at the dependencies of an application. Usually this is because of some setting that's been hard-coded and accidentally checked in. We had one customer who found that they couldn't run a particular application outside of their US offices. They couldn't understand why until they traced it with Breeze and found the dependency in someone's home directory. The home directories were not replicated outside of the US. My colleague who ran this application said he configured it to run 16 ranks across 2 machines. Let's check the arguments and environments to make sure that that matches. In this case, we can see the number of processes is 16, and we can see that the host file has been passed in. Now, this may contain 2 hosts, but we can't see any child traces here. Breeze can be configured to trace only the processes on the head node, but if we look down at the bottom, you can see all 16 ranks here. So that implies this application actually only ran on 1 node, not on the 2 that my colleague thought. I can check which machine it ran on by looking at the host name in the environment. Here you can see the name of the machine. I can check that that's the same across the whole trace by searching here. Here you can see all instances of the hostname variable, and you can see the name is the same every time. So we've verified that this application has 16 ranks and is running on one machine. If I was still unsure where the application was spending its time, then I could look at the duration view and sort by the total amount of data read or written, or perhaps more interesting, the total number of reads and writes. Here it looks like each rank does a little over 2 million reads and writes. We already saw those in the timeline view. And so what we verified here is that each of those 16 ranks does read and write to one file. So that means that although if we go back to the IO summary, although there was a little over a minute doing bad IO, that's in fact split over 16 ranks. So if that bad IO was removed, it would only in fact shorten the runtime by a few seconds. And the IO is going to the local file system. So again, it's not putting pressure on any shared file system. Improving the IO patterns is not likely to make any difference to any shared file system or to the runtime of any other application. Debugging problem applications involves a mixture of looking at the data in Breeze and combining that with the knowledge of your own application and how it's meant to behave. You can use the network view to look at any network connections to license servers or object storage. Here you can see our connections to license servers. If the application is taking a long time to connect to the license server, you could see that here. We had a customer who brought their HPC infrastructure to a halt because a license server went down, and the network timeout to connect to that license server was about the same length as the frequency of the license check. And so the application spent their entire time hanging trying to connect to the license server. Finally, let's take a look at the IO over time, looking at bytes read from the root file system. That most of the data is read right at the beginning, with a small amount of data read throughout. If we switch to read, the number of reads is consistent with what we saw, but we know that in fact most of these are reading a very small amount of data. If I was concerned with the performance of the file system, or if I was benchmarking a new file system, then I would be able to look at file system IO latency here. This histogram down at the bottom shows the minimum, maximum, and total amount of time spent doing IO, in this case reads. If I switch to the root file system, the reads are relatively fast, this being a local file system, but I bet if I look at the user directory, which is a shared file system, you will occasionally get much longer reads and writes, and there is a read that took 12 milliseconds. That's not uncommon for shared file systems. Breeze can't explicitly tell you when an application is getting a cache hit or a cache miss, but it is safe to assume that anything in the sub 10 microsecond range is a cache hit and is coming from local storage, whereas anything taking longer than a millisecond is certainly going over the network, possibly to spinning disk. I hope you've enjoyed this advanced tour of Breeze. Thank you for listening.